Retinoscopy is an essential technique used by optometrists to determine a patient's eyeglass prescription. It involves shining a light into the patient's eye and observing the reflection or reflex off the retina. This reflex provides valuable information about the eye's refractive error, which is the degree to which the eye can focus light onto the retina. Retinoscopy is considered an objective measurement, meaning it does not rely on the patient's subjective responses. This makes it particularly useful for children and individuals who have difficulty communicating their visual needs. By carefully analyzing the movement and characteristics of the retinal reflex, optometrists can determine the appropriate lens power needed to correct a patient's vision. Retinoscopy is typically performed in a dimly lit room with the patient looking at a distant target. The optometrist uses an instrument called a retinoscope, which projects a streak of light into the patient's eye. By adjusting the lenses within the retinoscope, the optometrist aims to neutralize the movement of the retinal reflex, indicating that the light is being focused correctly on the retina. The information obtained from retinoscopy, along with other tests, helps the optometrist determine the patient's refractive error and prescribe the appropriate corrective lenses if necessary. This objective measurement forms the foundation for clear and comfortable vision. Gross retinoscopy is the initial measurement taken during a retinoscopy examination. It involves determining the lens power required to neutralize the movement of the retinal reflex at a specific distance, typically at arm's length or about 67 centimeters. This measurement provides a preliminary assessment of the patient's refractive error. To perform gross retinoscopy, the optometrist uses a retinoscope to project a streak of light into the patient's eye while observing the reflex through the pupil. The optometrist then introduces lenses of varying powers in front of the eye, carefully observing the movement of the reflex. The goal is to find the lens power that neutralizes the movement, creating a reflex that appears to stop or stand still. The lens power required to neutralize the reflex at this distance is recorded as the gross retinoscopy measurement. For example, if a +2 diopter lens is needed to neutralize the reflex at 67 centimeters, the gross retinoscopy would be recorded as +2. It's important to note that the gross retinoscopy measurement represents the refractive error at the working distance, not at infinity, which is the standard for eyeglass prescriptions. Therefore, further calculations are necessary to determine the final prescription. Net retinoscopy represents the patient's refractive error at infinity, taking into account the working distance of the retinoscope. To calculate net retinoscopy, we need to adjust the gross retinoscopy measurement to account for the difference in distance between the retinoscope and infinity. The adjustment factor is based on the working distance of the retinoscope. At a typical working distance of 67 centimeters, the adjustment factor is -1.5 diopters. This value represents the lens power required to focus light from infinity onto a point 67 centimeters away. To calculate net retinoscopy, we simply subtract the adjustment factor from the gross retinoscopy measurement. For example, if the gross retinoscopy is +2 diopters, the net retinoscopy would be +2 minus 1.5, which equals +3.5 diopters. Net retinoscopy provides a more accurate representation of the patient's refractive error at infinity, which is essential for determining the appropriate eyeglass prescription. However, it's important to note that net retinoscopy is still an objective measurement, and may not always align perfectly with the patient's subjective visual experience. The final prescription represents the lens power required to provide the patient with clear and comfortable vision at all distances. It is determined by considering the net retinoscopy findings, subjective refraction results, and the patient's individual needs and preferences. While net retinoscopy provides a valuable starting point, subjective refraction is crucial for fine-tuning the prescription. During subjective refraction, the optometrist presents the patient with different lenses and asks them to report which lens provides the clearest vision. This process helps to refine the prescription and ensure that it aligns with the patient's subjective visual experience. The optometrist also considers the patient's lifestyle, visual demands, and any underlying eye conditions when determining the final prescription. For example, a patient who spends long hours reading or working on a computer may require a different prescription than someone who primarily engages in outdoor activities. In some cases, the final prescription may differ slightly from the net retinoscopy measurement based on the patient's subjective responses and individual needs. This highlights the importance of combining objective measurements with subjective feedback to achieve the best possible visual outcome.